In this section, we're going to talk about resistors, which are very important and omnipresent components in electronics. We'll define what is resistance. We'll talk about resistor in series and in parallel. Let's look at a little example. Let's say we have a circuit like this one represented on the right. We have a battery, so it's a voltage generator. Let's say this battery is a 1.5 volt battery. And then what we connected here to the circuit is a piece of material. So it could be anything. You could connect wood, you could connect metal, or really anything you want. So as a result of the 1.5 volt applied to this material, we're going to have a certain current I going through the material. And again, as described before, if you do the ratio between the voltage 1.5 volt in this case and the current, you get the resistance of the material. The resistance of the material represents how much the material opposes to the passage of electrons. So in this case, we have a battery. So as we said before, the anode of the battery is full of electrons. These electrons really want to go to the cathode of the battery, which is the positive terminal. Now we have a closed loop, a closed circuit here, so it's possible for this electron to go and reach the cathode. So what's going to happen is that the electron is going to start to travel, go through this ideal wire here, reach this material. Now inside of this material, the path of the electron is probably not going to be straight, because the material itself is made of atoms. So as the electron is trying to go through the material, it's going to bounce around. It's going to hit an atom, change direction, do something like this, so bounce a little bit around. But eventually it's going to find its way out and it's going to reach the cathode. Let's try to understand the difference between power and energy with another hydraulic example. So here we have a little system with a cistern. Cistern is a big tank full of water, and this big tank is at a certain elevation compared with the turbine, and let's call this different in height h, and let's say that is equal to 100 meters. Then we have a valve that can be open and closed, so allowing the water to flow down through the turbine, and the turbine is just a device that can be used to convert the energy of the water into electrical energy, for example to power a house. Now let's do a little bit of a calculation to see, first of all, what is the energy that is stored into the system. As we've seen before, because we have a certain amount of water with a certain mass at a certain elevation, that is equivalent, that means that the water will have a certain potential energy, in this case gravitational potential energy. So here we have a few numbers, let's just do the math. So we have been told that the volume of the system is 10 cubic meters. So as a consequence, because this is water, we have a weight of 10 tons, so 10,000 kilograms. So now the energy, U, it's equal to mgh, where g is the gravitational acceleration, which is roughly equal to 10. So if you substitute, so the mass is again 10 ton, g is about equal to 10, and h is about 100. So in the end, what you get is about 10 megajoule. So this is the energy that is stored into the system that can be used to produce a certain amount of work. The way you produce the work in this case is by opening the valve, letting the water flow down, and turn the turbine so that the energy can be converted into electric energy. Now, let's say we have a certain flow of water that is equal to 1 cubic meter per second. So when you open the valve, you have 1 cubic meter per second of water coming down. So now, in this way, we can easily calculate what is the power that is transferred from the water to the turbine. So we have 1 cubic meter per second. Now this cubic meter, each of the cubic meter has a weight of 1 ton. And then we can multiply by the acceleration of gravity and the height. So in this case, you see, it's kind of a similar equation. We have the mass, we have the acceleration, and we have the altitude, and all of that divided by second, meaning this is an energy that we are transferring every second. So this is equivalent to, if you do the math, 1 megawatt. So this is the amount of energy that is transferred every second from the system through the turbine. So in this case, because we have 10 megajoule and we are delivering a power of 1 megawatt, that means that after 10 seconds all the energy will be consumed. What is a resistor now? A resistor is an electronic component that is specifically designed to have a certain resistance. So a resistor usually in schematics have this symbol here. Sometimes when I draw by hand will most likely look more like this, just because it's kind of hard to make this shape. But it's a very simple component to use and to understand. As we said before, you put it in a circuit. If you know what is the voltage across the device, you can calculate the current very easily by dividing the voltage by the resistance. And vice versa, obviously. If I tell you what is the amount of current going through the resistor, you can immediately calculate the voltage across the device by multiplying the current by the resistance. Down here, there is an example of a resistor, just in case you ever open an electronic device. This type of resistor are called through-wall. They are not the latest and most modern components because they're quite big, but they're still used in the industry quite a bit. In order to push electrons through a resistor, you need to spend some energy. So this energy is initially in the form of potential energy, as if you remember, the voltage across the resistor is basically a representation of the potential energy that the electrons have. The potential energy is converted into kinetic energies, and that's how the electrons are pushed through the device. But then, as the electrons go through the resistor and hit the lattice of the material, they will convert the energy into thermal energy that will increase the temperature of your resistor. So if you take a circuit without a battery, and nothing is connected, there's no current, you measure the temperature of your resistor, and then you connect a battery to it, and all of a sudden you have a current going through the resistor, you wait some time, you measure the temperature of the resistor again, you will see that the temperature of the resistor is increased. The first time we talked about current, we made an analogy between current and a water stream. It's an analogy that works really well, as you can think at the current as a stream of electrons. Now we're going to extend that analogy to include also the voltage and the resistance. This analogy should help you understand better these concepts. Let's talk about the hydraulic circuit first, on the left on the slide. At the bottom we see there is a reservoir of water. You can think of this as a big lake or an ocean. Simply is a place that has so much water that no matter what you do with your little circuit, you're not going to be able to influence it at all. Close to the reservoir there is a low pressure, and this is a characteristic of the reservoir as well. Again, because this is directly in contact with the reservoir, if the reservoir happens to have a low pressure, all the rest of the circuit in direct contact with the reservoir is going to have a very low pressure as well. There's no way you're going to change that. Then we have a pump. The pump is able to change the pressure from low to high. That's exactly the goal of the pump, to apply a certain pressure to the water so that the water will actually flow through your circuit. Then your circuit is simply made of a big tube with pretty big cross-section, so the water is really free to go around your circuit. But then you see that at some point here you actually have a choke, a point where the cross-section of the tube becomes much smaller, so it's going to be much more difficult for the water to go through that. You can say that this choke is applying a resistance to the flow of the water. It's pretty easy to understand what is the electric equivalent of this hydraulic circuit. The flow of the water, it's clearly the current, equivalent of the current. The pressure is the equivalent of the voltage. So we have low pressure, low voltage, and high pressure, higher voltage. The pump is the equivalent of a battery, like a device that is able to change the pressure from one point to another. And the choke is the equivalent to the resistance. So we have the equivalent circuit here on the side. We have a battery, again, which is equivalent of the pump, high voltage at the top, low voltage at the bottom, a resistor in between, and we know that through the Ohm's law, we are able to calculate that the current that will flow through the circuit will be equivalent to the difference in voltage divided by the resistance. At the same time, the flow of the water through this hydraulic system is equal to the difference in pressure divided by the resistance. Not all electronic circuits can be explained using the water analogy. For now, this water analogy is very useful to understand in an intuitive way the relationship between voltage, battery, current, and resistance. Real circuits are much more complicated than the one that we are dealing with for now. Usually they are made of many more components. So it's really important to learn a few tricks that allows you to simplify the circuits, or even just to understand what's going on even when there are a lot of components. The circuit on the left has 4 components. There is a voltage generator, and there are 3 resistors, R1, R2, and R3. These 3 resistors are in series with each other. The same current will go through the 3 resistors, because obviously just looking at the circuit there's really no other way to go for the current. In the middle of the screen we have another circuit where we replace the 3 resistors with an equivalent series resistor. So what we're trying to do here is we're trying to simplify the circuit, and we're trying to find what is the value of R series that for the same voltage V, so the exact same battery is applied to the R series resistor, will give us the same current as the series of R1, R2, R3. So we really try to simplify the circuit. If the goal of the 3 resistor was to generate a certain current from the voltage of the battery, or if we replace the 3 resistor with an equivalent resistor, nothing is really changed. In order to calculate the equivalent series resistance, we'll have to use Ohm's law and the Kirchhoff voltage law. The way we're going to do this is very simple. We have V, we have I, and we have R1, R2, R3. So V is an input because it's the battery that we placed here. What we want to do is we want to, from these circuits, from the original circuit on the left, we want to calculate the values of I. Of course, we're not going to be able to calculate the value in terms of amperes, because we don't have the value of the voltage, we don't have the value of resistance, so we will never know the actual value of the current. Our goal is to calculate I as a function of V, R1, R2, R3. In order to do that, the first thing we want to do is to give a name to the voltage across the 3 resistors. So because the resistors are called R1, R2, R3, we're going to call the voltage V1, V2, V3. The orientation of the arrow of the voltage is random. Of course, I know already what is the result, so I put the smart way to put this the orientation, but even if you place it upside down, you can still get the right results if you follow the Kirchhoff voltage rule. So anyway, just random orientation from the top, and that's it. So now, using Ohm's law, I can write the value of V1 as a function of I and R1, because V1 has to be equal to R1 multiplied by I. And for the same reason, V2 is equal to R2 multiplied by I, and V3 equal to R3 multiplied by I. Very simple. So now, if we use the Kirchhoff voltage law, like this, I can decide a certain random orientation. It's very easy to write that V has to be equal to V1 plus V2 plus V3. So now you can see that here we have all the elements, right? We define V as a function of V1, V2, V3, and V1, V2, V3 has been defined as a function of R1 and R2, R3 and I. So now if we replace V1, V2, V3 with the definition of V1, V2, V3 from these 3 equations, we get the V is equal to R1 multiplied by I, R2 multiplied by I, plus R3 multiplied by I. Now we can collect I, because this is, we have the sum of 3 terms, and all 3 terms have I. So if we collect I, we obtain R1 plus R2 plus R3. If we do this, very easy to calculate what is the value of the current as a function of V, R1, R2, R3. So the current I will have to be equal to V divided by R1 plus R2 plus R3. Now, what we're trying to do with this exercise was to find a value for the resistance R series that will give us the same current for the same voltage applied V. It's very easy to see from this very equation that the value that R series has to be to give you the same current I is equal to R1 plus R2 plus R3. So R series will be equal to R1 plus R2 plus R3. To conclude on resistor in series, here we have like a generic statement that you can keep in mind. So let's say you have a certain number of resistors in series. So in this case, I'm assuming, from R1 all the way to Rn, So it doesn't matter what is n, and it could be 100, it could be 1000, it doesn't matter, you can sum as many as you want. The series of a certain number of resistors is equivalent to a single resistor whose value is equal to the sum of the value of all the other resistors. So in this case, all these resistors in series will be equivalent to just one resistor called R series, whose resistance is equal to R1 plus R2 plus R3 plus all the way till Rn. Let's now look at what happens with the resistors in parallel. The circuit on the left, there are two resistors, R1, R2. In this case, they are not in series, but they are in parallel. Components that are in parallel share the same voltage. That is fairly easy to see. Voltage is defined between nodes of a circuit, and here we really only have two nodes. One node is this one, node A, and the other node is this one, node B. You see that between these two nodes, you can only define one voltage between these two nodes. So automatically, the voltage V that is generated by the voltage generator or a battery is going across both R1 and R2. Now, depending on the value of R1 and R2, we can possibly have different currents I1 and I2, or they could also be the same if R1 and R2 are the same value of resistance. What we want to do here is exactly the same as what we did before for the resistor in series, which is we want to find the value of R parallel, the value of a single resistor that has the same effect as the two resistors R1 and R2 in parallel. From a point of view of the voltage generator V, whether there are two resistors, one resistor, 1000 resistors, a mix of series and parallel resistor, it doesn't matter. The net effect of having two resistors on one resistor will be to generate a current I from a voltage V that the voltage generator had created. So from the point of view of the generator V, having one or two resistors doesn't make a difference as long as the resulting current I is the same. So what we want to do is exactly that, to find what is the value of our R parallel, as I call it here, that actually has the same effect as the parallel of R1 and R2. In order to do that, we will make use of the Ohm's law and also the Kirchhoff's law. In particular, we'll adopt a similar strategy as done before. If you take R parallel and you write it in terms of Ohm's law, what you can write is the following. R parallel is equal to V divided by I. So V is kind of like an input because it is defined by a battery. We don't know what is the value, but it's a certain number. I is really the incognita here, right? Because the I, it really depends on the resistor, R1, R2, and so on. So what we're going to do, similar to what we've done before, is that to use the circuit to the left, the first circuit, calculate the value of I relative to V from using the Kirchhoff's law and Ohm's law. And then once we've done that, we'll replace the value of I into this equation. Because I will be dependent on V, V will simplify, and in the end we'll just have a value of R parallel, which uniquely depends on R1 and R2. Currents, it's very simple. I1 is equal to V divided by R1, and I2 is equal to V divided by R2. So it's very simple. Again, we don't have any number here, but these are Ohm's law for resistance R1 and R2. It's basically the definition of how a resistor works. Now the second thing, to connect I1 and I2 that we just defined with I. So it's very easy to see what is the result, because it's a very simple circuit, but we can apply the Kirchhoff current law to be a little bit more rigorous. So what we do, we choose a node. Obviously, we can choose any of the nodes. In this case, let's choose this one. Obviously, it has to be a node where I1 and R2 go. A node used by I1 and I2. A definitely works well for us. And now we're just gonna write that it's actually very straightforward. I minus I2 minus I1 minus I2 equal to 0. So I'm summing all the currents entering the node and subtracting the one leaving the node, everything equal to 0. And this simply tells me that I is equal to I1 plus I2, which is kind of obvious if you look at this and you think at the water equivalent. The water I, or the current I, is coming into the node. There are two currents coming out of it, so the sum of these two currents has to be the same unless some electron got lost in the way. So now the final part, it's very similar to what we've done before. The equation of I is a function of I1 and I2, but I1 and I2 are defined by the Ohm's law, so we just rewrite the same thing, but just substituting the expression for I1 and I2. V divided by R1 plus V divided by R2. So we have taken these two equations and this equation and combined into one. And now we're very close to the end. As we discussed before, R parallel is defined as V divided by I. Let me just call it RP. V divided by I from the second circuit here. From here you can tell it's V divided by I. So the V is the same as the one in the previous circuit, and it is an input, so there's really no other way to break it down in smaller pieces. But I, it's a function of R1 and R2, which in turn are a function of R1 and R2. So now we'll just replace I with the new definition of I that we found. V divided by R1 plus V divided by R2. Obviously, you can see that we have V at both numerator and denominator, so that can be simplified. So the final equation that we obtain is the following. Where this part at the end, this is the value of the equivalent parallel resistor. In this slide I summarize the final result, the final equation needed to calculate the parallel of resistor. Again, on the left we have an hypothetical circuit with n resistor in parallel. The number of the resistor can be any, it could be 100 resistor, 10 resistor, 3 resistor, doesn't matter. And on the other side we have the equivalent parallel resistor, and this one is the equation that you need to use to calculate it. So as we've seen before, the way you do it is you take the inverse of each of the resistance, you sum all the inverses, and then you do the inverse of the whole thing. So this one is a little bit more complicated than this resistor in series, but I mean, not too much, it is manageable. Also, many times you won't really have many resistors in parallel. Many times it will just be 2 resistors most of the time. So there is a simplified version of this equation, like if you just have 2 resistors in this, so you only have R1 and R2, and you kind of play a little bit with the math. There is like an easier version, at least easier to remember. So R parallel in that case become R1 multiplied by R2 divided by R1 plus R2. So this one is a little bit easier to remember, at least for me, and honestly it's the one that you use most of the time. I want to stress a concept that is really important before we move on. What does it mean equivalent here when we say equivalent parallel resistance? Because obviously if we take this circuit and change it into this one, the circuits are not equivalent anymore. We even have a different number of components. How could they be equivalent? What the equivalent word means is that this network of components behave exactly the same way as this individual component from the point of view of the external circuit. So this, it's a little bit of a mouthful, but let me just explain with a very simple circuit. So if we have a battery generator connected, our usual battery generator, you could see this network of resistances as one big component. Now the battery source, the voltage generator, doesn't know what it is connected to. The only thing it knows is that it applies a voltage across these components. So you have 0 volt here and V volts here, and as a result of that there is a certain current I that is requested out of the voltage generator. From a point of view of the voltage generator, whether this component is made of n resistor or it's made of just one resistor, there's no difference as long as the required current is the same. There's no way this voltage source has a way to understand that there's only one resistor instead of 10. So this is what the equivalent word means. It's equivalent from the point of view of the rest of the circuit. Now, if you consider the overall circuit, obviously these two circuits are not equivalent anymore. Here we have n plus 1 components, including the battery source, the voltage generator, and in the other case we will only have two components, the voltage source and the parallel resistor. So this is a really important concept. The equivalent parallel and serial resistance is a very useful concept. Most of the time it's just used to simplify the mathematical calculation, because if you knew what is the equivalent value of this parallel resistor, it will be much easier for you to calculate the current given a voltage. Whereas if you don't know what is the equivalent parallel resistance, every time I change the voltage, to know what is the current I, you will have to calculate the current in each of the resistor, then sum it up all together, and then you can tell me what is the value of I. So that is one of the usage of the equivalent parallel and serial resistor. Other times you might actually calculate the value so that you can replace many components with a fewer number of components, but it's very important to stress that that is not a must. Doesn't make necessarily a circuit better than another. Each case is different. In this lesson we're going to talk about type of resistors. The first thing we want to talk about is the termination type. So we have two big categories of resistor here: through all components, which sometimes is abbreviated with TH or PTH, where P means plated. And the other category is surface mount components, which is usually abbreviated as SMD, surface mount device, or SMT, surface mount technology. Here we have an image of a through-hole resistor. As you can see, it has this little shape, kind of like a sausage shape, and it has many little colored rings on it. So these rings are used to determine the value of the resistor and also to communicate the tolerance. Now, another important thing is just to kind of explain the name of this category of resistor. You can notice that they have this through-hole resistor, they have these leads that are very easy to bend. So the way you assemble this on a circuit is the following. So let's say this is your board, your electronic board. You're looking from the side of the board. So, you know, the board kind of continues like this. But let's assume we look from the side. Now you take your resistor, and so this is kind of your resistor. And then what you do is that you take the leads, you bend them, and you make them go through the board. That's why they're called through hole, because they have these leads that goes through holes in the board. Then what you do is that you take your soldering iron and you solder the other side. Obviously the leads normally are much longer than this, so they continue going, but after you solder them, you just trim them, because you don't want to have leads hanging on the other side of the board, which are not doing anything anyway. So that's how you assemble it, and that's how we justify the name of this category of components. Another thing I want to highlight is the 1/6 of a watt indicated here. This is the so-called power rating of the component. And what these numbers is telling you is that you want to make sure that your circuit, the way it is designed, is such as the maximum power that is going to be dissipated on the resistor is always going to be lower than this number, so that everything will work fine. Because if the power becomes higher than this value, then the component will overheat and eventually it will break. In this lesson we're going to learn how to read the value of a resistor using its colored band. So we're talking about through-hole resistors here, and we're going to use this table to determine the value of the resistance and the tolerance. A resistor can have 4 bands or 5 bands code. Let's start with the 4 bands, that is the simplest. So in case of the 4 band, you can notice right away that the bands are split into groups. We have first 3 bands in a group all the way to the left, and then we have another band that is isolated. So the first 3 bands are used to determine the value of the resistance, and the last one will be used to determine the tolerance. So if we start with the first group, the first bands, so all the bands but the last pretty much, they need to be taken at face value. What do I mean here is that you look at this table and you see that green always means 5 and blue always means 6. So because of the 2 first bands, so this will be part of the actual value of the resistance. So we do 5 and 6. The last band of the group, you might be inclined to say, well, the last one is yellow, so the value is 4. So is it the 564 ohm? No, the last one of the group always needs to be used as a multiplier. So in this case, the multiplier is 10 kilo. So the 4 is actually applied to 10 as a power. So what you're basically doing is multiplying by 10 to the power of 4. And what you get out of this is 560 kilo. So that's the value of the resistance. Now the last band, the isolated one, it's gold. That's the most common value that you will, color that you will find for the tolerance. And that means that the tolerance of this resistance is plus minus 5%. So that means that as you buy these components and you put it on the board, the nominal value is 560 kilo, but really the value of the resistance could be anywhere within 560 kilo plus minus 5%. Now, if you look at the 5-band code, this one is exactly the same concept. Even here you can distinguish the bands between two groups. There are 4 bands in a group together and one that is isolated. And just as before, for the first group, the first bands has to be taken at face value. So we have red, orange and violet. So red is 2, orange is 3 and violet is 7. So it's a 2, 3, 7. And then the last band of the first group is the multiplier. So in this case it's black, so the multiplier is 1 ohm. So in this case, the value of the resistance is actually 237 ohm. And then the last band, which is the one that is isolated, is again the tolerance, which as you can see here, brown is equivalent to plus minus 1%. So the final value of the resistance is 237 ohm plus minus 1%. The second category of termination type for resistor is the surface mount type, SMD, surface mount components. We have an example here. This is by far the most common type of termination for resistors in modern electronics. It's not difficult to understand why. So this component is really tiny. For example, this one, 1206, is the indication of the package. So a 1206 component is a component that is, like if we draw it like this, the 1206 is 3 by 2 by 1.6 millimeter. So just like this, 3 by 2, 1.6, and these are millimeters. And this is one of the biggest dimensions for SMD components. You can go all the way to the package that is 0.1005, and in this case the dimensions are 0.2 by 0.4 millimeters. So really tiny. These components are not assembled the same way you assemble the through hole, obviously, but as the name implies, they are mounted on the surface of the board. So let's say if this is the side of the board, what you do this time is that you drop your component here like this, and then you're just going to solder here and there. So it's completely sitting on the top, it doesn't require holes in the board, and is mounted on the surface. So that explains the name. We see that this component is a 100 ohm resistance value. So the way you determine that for SMD, there are 2 ways. So if the component is big enough to actually have digits on the surface, the number is represented in this way. Like in this way we have 101, which indicates 100 ohm, because usually the first digits are a representation of actual digit of the value of the resistance, so 1 and 0, and then the last digit is usually a multiplier. So it means, in this case, it means that you have to take 10 and you multiply by 10 to the power of 1, where 1 is the last digit. So in this case, 10 by 10 is equal to 100 ohm. So for example, if this was 102, that will indicate 1 kilo, because it will be 10 multiplied by 10 to the power of 2, which is 100, so you get 1 kilo. The reason the number is represented this way is pretty obvious. You will never have enough digits available on the body of the component to be able to represent, the biggest number of resistance. When the package becomes too small, like in the case of a 01005 or 0204 or those kind of size of 0201 size of package, then in that case you don't even try to write the value of the resistance on it. So in that case the components look all the same and you just really have to know it. So you have to take it correctly, or you can always take a multimeter and measure it. Now the 2 resistors that I introduced before, this one and this one, they differ because of the termination type. But they were, in both cases, these were fixed resistor. So that means that the value of the resistance shouldn't change, at least at the first order. Now, this is not a perfectly accurate explanation, because the resistance does change a little bit based on several factors, like the temperature, but the change should be pretty small, and it's an unwanted change. It's just something you have to deal with. But at first order, kind of the big picture is that the value of this resistor shouldn't change very much. There are other type of resistors, of components that are built to be variable resistors, and these are called potentiometer. So you see two examples of potentiometer here, and as you can notice, there is a handy knob that can be used by the user to turn and do something to this component. We're gonna figure out exactly how this works. But these are the type of components that you will find in circuits wherever there is a need for a user to operate a certain knob to do something to the circuit. For example, if you have a stereo, you know you're gonna have a knob that you can turn to change the volume of the music, for example. And in that case, most likely a potentiometer was implemented to allow the user to apply this rotation movement and change some parameter. Let's try to understand how this potentiometer works. I'll start with an example. Let's say you're building a resistor and you want to build this resistor this way. So you have the wire coming in, and then, as we know, a resistor is a component that opposes to the passage of current. So you find some material that has this property, it opposes particularly well to the passage of current. And then you define your, you take a piece of this material, and based on the geometry of these pieces of material, you get a certain value of resistance. For example, let's say 4 kilo. The question is, what happens if I take another pieces of wire and connect it in the middle and I make it available from the outside? Well, what happens is very simple. So if I want to draw the symbol of this, we went from one single resistor with 4 kilo. Now we have two resistor equal to 2 kilo, and we have a terminal in the middle. So in a way, we built a sort of a voltage divider here. Now, what happens if I move this central terminal that is actually not fixed, but it can be moved, and I move it to 3/4 of the way from the bottom? So now it's pretty simple to understand what's going on. The resistance for the current from the entry point till the output of the central terminal is much smaller than the resistance from the central terminal to the lower terminal. So now we're gonna have 1 kilo here and 3 kilo at the bottom. So you see two fundamental things here. No matter where you place this central terminal, the total sum of the two resistance has always to be 4 kilo, because that is completely determined by the material I pick and the dimension, the geometrical dimension of the material. And the other thing is that depending on where I position the central terminal, I will break down this value of resistance differently between the upper and lower resistance. If we go back looking at this potentiometer picture that we have here, it should be easy to understand why they have 3 terminals instead of 2. As we just said, we have the first 2 terminals, terminal 1 and terminal 3, for example. So the one top and bottom are just connected. Between them there is a constant resistance. And then there is another terminal, which is the terminal number 2, the one in the middle, that is actually a special terminal that taps the resistor, the internal resistor, in different positions, so it can move up and down depending on the position of the knob. So again, the resistance between 1 and 3 is always constant, but the resistance between 2 and 1 or 2 and 3 completely depends on the position of the knob. One of the reasons to use a potentiometer is, for example, to get a variable voltage divider. So a voltage divider works the following way. Let's say if we take this one, which is a voltage divider, we have V in here, the input voltage, and then we have R1 and R2, and this is V out. So V out is equal to V in multiplied by R2 divided by R tot, where R tot total is the sum of R1 and R2. Now, in case of a potentiometer, R tot is constant and depends on the value of the potentiometer that you buy, but R2 totally depends on the position of the knob. So pretty much from a constant input voltage, you can get a varying output voltage that goes from 0 all the way up to V in, depending on where you position your knob. The schematic symbol of a potentiometer has to be something different than this, because otherwise it will be indistinguishable between the voltage divider. And this is also does not represent it well, because it does not contain any information on the fact that R2 and R1 are variable depending on the knob position. So the potentiometers, they have a dedicated symbol, which is the following. So you have the symbol of a resistor plus an arrow to the middle of it. So that's pretty simple to understand. The top and the bottom here are terminal 1 and 3, and the one in the middle is terminal 2. So you know that the resistance is constant between 1 and 3, but it can change between 2 and 1 and 2 and 3.